we do this? Oh, recording in progress. Great. Oops. Sorry. Yeah. So all these things started from my attempts to understand the classical result, now classical result about effective dimension. And this result about effective dimension says that what are the dimensions of point on a line? But let me say more about this. What is dimension? So if we have some real number or some point in two-dimensional plane or whatever, of course we cannot define the complexity of these things because it's infinite. So what we can do, we can study how the complexity of 2 to the minus n approximations grows when n increases. And so we can, one of the simplest way to do this is just to take a representation of the number and take complexity of first n bits divided by n, and then you take the lim. And the question is which lim you take if it's not converging. You can take lim inf or lim sub. And lim inf is called effective Hausdorff dimension. And it's related to geometric measure theory in a very nice way. This is called point to set principle and so on. But for now, you can think about this. And it's reasonably invariant. So if we change the base, or if we apply some computable diffeomorphism of some open set, it is the same, and so on. And this is for a point. It's of course between 0 and 1. And if we have a line. For numbers, it's between 0 and line. If we have a two-dimensional point, then we have two things, and we can consider also effective dimension for points is between 0 and 2. And if we have lines, which is ax plus b, then of course it's just a point in a dual space. So we can also consider so we have point, number, and line. We also have something between 0 and 2. So it's well-defined thing. And if it's, I wrote here 0, but if there is some number, if x is not between 0 and 1, or a point is far away, still it's somehow finitely far away. So how it doesn't really matter for the lim inf how we take into account the complexity of the initial the part before the decimal point. So this is the notion of dimension, and this is a result. If we have a line, imagine on a plane, we have a line of dimension L. So it's between 0 and 2. And then we consider different points on the line. So what are the possible complex dimensions of these points? And there is an answer that if L is smaller than 1, then we get all points between L and L plus 1. And if L is greater than 1, then L plus 1 becomes too big, and so we have all points in the interval between L and 2.
The statement is that this holds for any line of complexity L, there will be points like the interval of possible values of complexity is exactly this. Dimension.
No, of course, line can have simpler points. For example, line can go through 0. Why not? It will have some small if line goes through 0, there is a point 0, 0. Oops.
So what's the statement then? Happening? Can you repeat, please?
All this. What is What is happening? Oh God. Delete from. The statement is that all numbers here are possible as the dimensions of points.
Possible for which line? For every line or for some
For
lines?
every line of dimension L,
there exists a point.
If L is smaller than 1, all points for every possible number between L and L plus 1, or between L and 2, depending on what is L, there exists a point of corresponding dimension.
Excuse me once again, what's the dimension of a line?
Dimension of a... So, what is dimension of a point is clear or not?
It is clear.
Yeah, so the line is just, we can identify the line with the pair of its coefficients, A and B. So a line corresponds to a point AB.
Okay, thanks.
It's like in projective geometry. Actually, in projective geometry we have lines are just lines, two-dimensional subspaces, and points are one-dimensional subspaces, and there is one-to-one correspondence between two-dimensional subspaces, one-dimensional subspaces. We can take the orthogonal line to a plane and orthogonal plane to a line. But for that you don't need to worry. Just it's a pair AB now. And now.
For the most complex pair AB, or what do you take?
So say it again.
Do you take the supremum of the complexity of the pairs AB, or the maybe simple and more difficult ones?
No, if there is line, it is just have this equation with some fixed A and B.
Yeah, but you could also write it differently, right?
No. If we take line AX plus BY plus C is equal to 0, then we have some variability. But we can, we can assume that something is something is 1, and consider just A divided by C or B divided by C, or here we consider that B is 1, and of course, there are some lines, for example, vertical lines do not have this form, but vertical lines are more or less trivial, so it's not that important. No, actually, the idea is that if we have any natural manifold in standard sense of differential geometry, I don't know, the Lie group of all unitary transformation of something, or just well-defined manifold, then the points have some specific complexity, specific dimension. And we can use more or less any reasonable map for that, because if two maps are transition function is computable, as it usually is with natural maps, then the dimension is preserved. So everything in our world, after we fix a coordinate system somehow reasonably, has some dimension.
Okay, question.
Yeah.
So there's example that does not work. So I missed something. So imagine we take random line through origin. So dimension of line will be equal to 1, right?
Dimension of line will be equal to 1.
Yes. And the origin
so
is
the
on
theory
this
says
line.
that we can find any point of dimension between 1 and 2.
So the theorem is maximum dimension of point on the line, or
Not
every
maximal.
point.
We claim
sorry,
that
okay.
no, the maximal. First, let's say something about the maximal dimension.
That's what happens
the
when you don't write
dimension
the statements of theorems. I already asked
line
the question.
of complexity of dimension L has all points of all complexities between L and let's write it in one formula, L plus 1, 2.
Any line.
Any line. No, any line has some dimension. So we can
Just
apply the theorem to any line.
quantification over lines.
Yeah.
Probably the statement is clear.
Statement is clear. No, there are two things. Maybe so. Two things that I don't know. I tried to understand the theorem, but I failed. And all what I will trying to tell you today came out of this of some attempts to understand the theorem, but I failed. And so, if anyone knows how to explain this theorem, this would be great.
What was the
Yeah,
reference?
Sasha, I can try whenever if
Oh,
you want to
great.
jump in. Yeah.
Great. Okay. You are. No, of course it was a trap for you first of all, but then the second question: can you say what is known about points of smaller complexity than L?
Yeah, so this is interesting. So for the higher range, so this is called the dimension spectrum of a line. So
Yeah.
we fix a line and we look at all the possible values of the dimensions of the points on this line.
Yeah.
And we kind of want to know what this set is. On the higher dimension, so looking at basically the interval that Sasha drew, this is like the higher end of the spectrum. This is known completely. We know that the dimension spectrum contains an interval of length 1 for every line. On the lower end, so you can ask what's the minimal dimension of points on lines. This is much more tricky because, for example, this line through the origin, this is going to have a unique, so a line with random slope through the origin is going to have a unique point of dimension 0. There's only
Because
one.
all other points determine the line.
Correct, yeah.
We can just draw a line through 0 and this point, and so all the points have complexity at least L, but one special point has complexity 0.
Right. There is some more known now, especially there's this major breakthrough in geometric measure theory on something called Furstenberg sets. And I haven't written it down, but I'm pretty sure that if you apply some of their theorems to this question, you can get better control on the low dimensional points on the line. You can say that, for example, you can have some bound of the form for some small alpha. There are at most, I don't know the exact number, maybe, I don't know, some dimension beta set of points whose dimension is less than alpha on this line. So there should be some theorems of this type, but the exact formula.
But do I understand correctly first that now the answer depends on the line, not only the complexity of the line? Because, for example, if the line of complexity of dimension smaller than 1 is vertical, then of course it doesn't contain any simple point.
Right, yeah, so the theorem is much trickier. Yeah, it's hard to get a statement that captured everything because there are these examples of vertical lines through the origin, or more generally, lines whose, for example, y-intercept is irrational.
Yeah.
So, all these things make having a full classification probably not possible, but you can get bounds based on the dimension of the line.
Yeah, but so the spectrum depends not only the complexity but on the line itself.
Yeah.
And then the question is, are there some lines for which we can compute the spectrum? What we can prove about the spectrum of all lines? And what are the strange examples? For example, there are some obvious things. For example, we cannot have two small points on the spectrum because they determine the line, and then therefore if there is a small point, it's 1 point.
But even this is a little tricky because now you can't have 2 points of low packing dimension, the lim sup. but you could have possibly countably many because they could all be out of phase.
So here is the difference between lim sup and lim. Okay. So actually, if you have too much free time, we will be extremely happy to hear your kind of tutorial on this with all proofs we can understand, like in buffet à volonté, as it says in France, everything you can congest. Sure. But now, what I thought when I see this theorem, that probably we should start with considering a finite case without this lim inf, and then somehow apply it to infinite case. And this thing failed in a miserable way, but still let me explain. So first, the finite case can be understood in different way. First option is we still consider real numbers, but just consider the complexity of 2 to the minus n approximation for some n, which is a parameter. And what we have a line whose equation on level n has some complexity. What are complexity on the same level of points on this line? And the second thing, which is also natural, we can consider some field f, which contains 2 to the n elements, or who has about 2 to the n elements, but we want to the field is given. So either way, it's easily computable, it has small complexity, or we use it as an oracle everywhere, so the field is given. And then we can consider just exactly the complexity of lines and points as complexities of two n-bit numbers, two elements of the field. So typical complexity of the point is 2n, or a line, and typical... So we can again ask the question for finite field. And it turns out that things are different here. So here, indeed, the results for effective dimensions, mainly due to Don, are similar. So what is his theorem? So if we have a point of complexity L, and L is smaller than a line of complexity of some complexity L, has points of all complexities between L and L plus n. So we have a field of 2 to the n elements. We can identify its element with strings with n bits, and a line is a pair of the strings, a pair of coefficients, and every line of complexity smaller than n has points of all complexities between this L and L plus n. No, of course, it may happen that it's not literally all complexities, because it may happen that all complexity are, even numbers. So it's with precision of log ns usually. And what is not known, at least to me, that if L is greater than n, we would like to have all complexities between L and 2n. And strangely, this fails. At least all tricks I know fail. But I guess I have no feeling that this is there is some inevitable obstacle. Maybe just I didn't try something simple, or it would work. And the goal of my talk is to convince some of you to prove the second part, so that at least one result will be more or less not finished, but self kind of self-consistent. So why don't we know, if we know it for small complexities, why don't we know for complexities like 2n? And partial thing is known. We can always get complexity 2n. This is always possible. But going from L to 2n is not clear. Okay. So the plan is now to prove these things, maybe even try to prove it in different ways, to show what the simple things that are known, and maybe to convince you to solve the difficult thing. Okay, is it clear what we are trying to prove? Kolya, is it okay or not?
Yeah, it's okay. I guess.
Yeah, anyone? Misha, Georgi, кто там? Who else? I don't see all the faces, but just say something.
Looks clear. The statement is clear.
Statement is clear. Okay, then I try to erase everything, because the problem with these boards is that it's difficult to erase. No, you can. Okay, let me try. I never was unable to find how to erase all things at the same time. No.
In usual whiteboard in Zoom, you can use different pages and don't erase
different pages. Okay,
Miro
here I can move like this.
Page. Yeah, you can move.
I can move like this.
I mean, I can even try to guess how to prove that every complex line has a point of complexity 2n, because the graph is expander and something like that.
Okay, wait a bit. I just want to draw the. No, I cannot draw. I can. So you want to start with the first thing. So let me say every. So we have a field
line.
f of size to the n. Every line of complexity L greater than n has a point of complexity 2n. Yeah?
Yeah. So I guess you should like you wanna say that.
And as usual, you assume logarithmic precision.
Yeah.
So let's consider a line that only have simple points. And we want to say that probably because of some expander properties, there's a few of them, and then we obtain a contradiction that there is a complex line.
Assume not, you say. Then consider the set of all points which have complexity 2n smaller than 2n minus some c log n for large c.
Yeah, and I mean, consider the set of all lines that only have these points. That only have, well, basically subsets of S, one can say.
Set of all lines, they are subset of S. And you want to show, using some expander property, that what?
There are a few lines like that. Less than 2, much less than 2 to the n.
Is much less than 2 to the n.
Because I guess if I have too
this
many
line
lines,
will have complexity.
Then their union will be greater than. It's like maybe there is even a simple
So there are three steps. First, the claim is that if a set of all points, it has cardinality smaller than log cardinality is smaller than 2 to the n by some c log n. And then you say, then consider the set of lines which are its subset. And you claim that its cardinality or its log cardinality is smaller than n.
Yeah.
This is a combinatorial statement for every point of cardinality which is a bit less than 2 to the 2n. The set of all lines that go through all these points, only through these points, has cardinality at smaller than n.
Yes.
And just say how this combinatorial statement implies the complexity statement.
So we assume for contradiction that there exists a line of complexity, large complexity that has only simple points from S.
Yeah, we consider the set S of all points with this complexity.
Yeah, but then all the lines have lower that are subsets of S has low complexity because you can just enumerate points from S, and then you just need to indicate the
So
index
first
of
we
the
can
line.
enumerate all points of small complexity, and then we also can enumerate the lines who go only through those points. We need to ensure that every point has small complexity, and this is a numerable property.
Yeah.
And so we know that there are many lines, and so each of them has complexity, small complexity. This is the scheme.
Yes.
And indeed, so is it clear how to get the complexity statement from combinatorial one? It's a standard argument, but let's go through it slowly if needed. So, Kolya, Misha, Georgi, what do you say?
I'm okay.
You're okay, but okay. Yeah.
Fine.
Fine. So, okay. But maybe you know how to prove the combinatorial thing.
I think I know, but maybe
but maybe somebody else know. Kolya, do you know?
I think we can either we use the spectrum, or we can just use how you say exclusion-inclusion formula.
No, I think it's enough just to use that two different lines intersecting at most one point.
Right. That's what I meant. So we take the union, assume that there are
So imagine we have 2 to the k lines going through S.
We lower bound the total number of points 2 to the k times.
So the total number of points is S is greater
2 to the k times 2 to the n, I guess.
If we take the union of all the lines, we count some points twice. So this is the first term of inclusion-exclusion formula. And then we get too much. To get something
minus to the k
from below, we need the second term.
To the k squared, I guess.
So we have at most 2 to the k square pairs. So we have intersection point. And so we have this number of intersections, and each intersection contains at most one point. So this is bigger than 2 to the n, 2 to the k, 2 to the n minus 2 to the k.
And now we see that if k is much smaller than n, then this is much smaller than 2 to the n.
No, we need to show that it is big. So we know that this is much smaller than 2 to the 2n. And we need to conclude that k is smaller than n. So we have an upper bound for the number of points possible, And we need to upper bound the
I mean, if k is
lines.
like n minus 1, so we get, I don't know, 2 to the n up to a constant, right? I mean, it's just,
Yeah. So there are here we need two cases. If take if 2 to the k is, I don't know, smaller than a half of this, then its term is only constant factor gives, so it's 2k plus n. And so we get number, we get a bound for k as what we wanted. So the number of lines is smaller than the number of points divided by 2 to the n.
yeah.
Yeah, and if k is big, then these things we can artificially decrease it up to this number, and we just consider not all lines but only some of them, and then we can get bound that 2 to the s is smaller than 2 to the n over 4, something like 2 to the n over 4.
I don't get this second part.
I mean, it's basically, it says that if 2 to the k is large, it's not possible. It's not possible
Why?
to the k, because if it's at least 2 to the n over 2, just let's consider, so just consider exactly 2 to the n over, I mean, essentially 2 to
No,
the
we
n
can
over,
apply exclusion not to all lines but to some of them.
yeah, to the to the first 2 to the n over 2 lines, and then they already give more than we have s.
So if you do it more formally, the correct statement is this: if the number of in this points in some set S is at most this one, then the number of lines entirely in S is smaller than 2 to the n, S divided by 2 to the n, and maybe with some constant of this. But it's important. If, of course, if we S is all points on the plane, which is exactly 2 to the n, then we have 2 to the n lines. We don't divide by 2 to the n. So this is an important combinatorial restriction. And Andrei can explain how to use expanders and eigenvalues and the inequality, the standard bound for the number of edges between two sets in an expander, and so on. So this also works.
Yeah.
Okay. So I think that at least one proof is finished. So any questions now? Okay. Strange why the site.
So, and I guess like something like that, you can get basically that low complexity lines have points of complexity.
Yeah, but
n.
by the way, yeah. By the way, the same argument, because so it's not clear. Yeah. Since we have divided by 2 to the n, the same argument says that if we have line of complexity L smaller than n, then there is a point of complexity L plus n.
I mean, it's just if k is, well, basically it's better to say, I guess, if I have complexity k, given what is written already, then it has a point of complexity k plus.
No, unfortunately,
n.
it's written inconsistently. Here is L and here is K. So We cannot
Yeah.
be consistent.
But okay, it's just
But
the
anyway,
point is
if
that
we
if I
have
have 2 to the L lines, then they more or less cover 2 to the L plus n points.
points and exclusion says that it's unavoidable. The lines we cannot economize on this because they have only one point in common.
Yeah.
Okay, so any questions about this combinatorial proof? And then let me try to give a complexity proof, because it's important, because the final result of Don can be proven by this argument, and I don't know any combinatorial proof. So it's important to start with line L of complexity. No, we have line L of complexity L, which is smaller than n, given. What we need, find a point x of complexity L plus n. So maybe you know this also. So what do? We have a line of complexity. Sorry?
Who are you asking?
No.
Everybody.
You know or not?
No, I don't know another proof.
You don't know another proof. So then I'm asking someone else, therefore. So who knows? So Kolya, what should we do?
I think we should pick an x coordinate of highest complexity, that is n, and probably the point with that x coordinate has complexity L plus n.
Okay, let's try this way. Let's take some coordinate of complexity n. But imagine that this coordinate has the same information as L itself. It is not good. So L has some.
I know,
L has
like
some
take independent
complexity
points from
L, and we can take n random bits of
So you have to take independent point of largest complexity somehow. So you take a
we
random.
what will be reasonable to try is take the conditional complexity to be n. So it should have complexity even when the oracle is known to be n.
Yes.
Yeah? Okay. So the complexity of pair XL is now n plus L.
Yes.
And actually, we can also note that the complexity of this pair is just the complexity of the pair X. Because when we know L, the point is the same as this first coordinate.
So you have large.
But
wait. You have two different x's. One is large.
Let's decide the big X is a point, and the small x is its coordinate.
Okay.
No, you say we should take a first coordinate, which not you but Kolya said that you should take the first coordinate which has maximal complexity, and we agreed that it's better to take a coordinate which has maximal complexity even with oracle L.
So you want it's enough to show that complexity of a line given
So
X.
we know that that's complexity of this pair. So we have L and separately we have x. So the complexity of this pair is n plus L, which is the same as the complexity of pair XL.
Yes.
But what we needed to show that complexity of x is n plus L. So we should prove that this is the same. So how do we prove it? Kolya, how do we prove it?
But probably it's not the case, because this means that line can be determined from x. But
this
I
means
don't
that
see
complexity
how.
of L given x is 0. No,
But
not 0, but log n.
But it's not, can't be derived from the fact that the complexity of x given L is maximal.
In fact, it can. Let me explain. So imagine how can we reconstruct line L x given? Do you have an idea how to find L? So we know, of course, that L should go through x.
And then we
But
know
there are
that it's
many lines that go through x.
complexity of
What should we do?
Sasha, and capital X is the point on the line. I'm
Capital
sorry.
X is the point on the line, yeah. No, which means the point on the plane, and line goes through this point.
And why the complexity of the pair little xl is the same as the complexity of the pair capital XL?
Because if we know the line L, then every point is determined by its first coordinate. So generally, of course, first coordinate can be simpler. But if we add L, then they are exactly the same information.
oh,
There are many lines passing through X. How it
Now, of course,
can
there are
be-
many lines passing through X, because there are 2 to the n lines passing to every point. But so we need to find L somehow, given X.
we only know that the complexity of the x coordinate of the capital X is given this line is large.
No, we have another things. I claim that this only line of complexity at most L that goes through X. X.
Line of complexity at most x.
So we know that complexity of line is some small l, and I claim that this is the only line that goes through X. Why? So why it's not possible that there are 2 lines of complexity smaller than L that go through X? We need to use, of course, the same property that the 2 lines have the unique intersection point. The question is, how do we use it now?
So number of intersection points is 2 to the power L squared.
I mean, I guess we can
Of
say
such
that then we can describe this x
The line
coordinate.
can be reconstructed, the point can be reconstructed as intersection point of 2 lines, yeah?
Yeah. I mean, I guess so. You given one point, you can actually describe this small one of the coordinate. Well, basically the whole point, I guess, by specifying the other line,
Yeah.
which
So
only
if we
needs
know L
complexity.
as prime, which has complexity at most 2L, we can reconstruct X and L, because L we know, and X is the only point of intersection.
Yes.
And it was chosen that this is n plus L. And we know that L is smaller than n. So we get a shorter description than possible. So we prove that every line of complexity smaller than n has a point of complexity L plus n. Is it clear?
Yes.
It is not. Sasha, Sasha doesn't believe me, I guess.
I do believe you.
So you agree with this?
Yeah.
And then maybe you can, I have a question now. So here we used in a way that L is smaller than n.
Yes.
And so we want to find if L is just a bit smaller than n, if it's n minus c log n, then we find a point of complexity 2n minus some c log n, some maybe other c. And imagine we have a line of complexities bigger than n. I don't know, 1.5 n. How can we find a point of maximal complexity 2n, again minus or log n? So we know that before we have this in combinatorial proof, but our complexity proof use the fact that as L has complexity smaller than n. How can we prove that even if complexity is bigger than n, we still have a point of complexity to n?
Okay, so we have, let's see what happens with this proof. So the complexity.
Nothing good, because we have 2L here, and now we cannot.
No, I mean,
compare
I
it with L plus
actually,
L.
I don't know. So yeah, I mean, I was thinking in other terms, but okay. So
this complexity proof has a strange obstacle where the combinatorial proof has no problems. Our complexity proof has stupid obstacle.
wait. Let's see. So you say probably, I don't know, we should take the point again, the coordinate with the maximal complexity, which is independent of L, of the line.
Yeah, that's good.
And then what we have to show in terms of complexity, like I have to, so.
But then there is a problem. If you take a point which is independent of L, you have something which is bigger than 2n here.
Yes.
And
It's
complexity of a point is of course at most 2n.
Yeah, so we have to
So
bound the
you
complexity
cannot
of
hold
L
that.
given X by not by 0, but something else. By 2 to the n
So
minus.
we need to show that the complexity of X given L is smaller than
2 to the n minus L.
L minus n.
N minus L. Why? L minus. Wait. How much? So we have.
Okay, maybe we have 2n.
We have 2L. And we need 2L minus n.
I think L minus n, yeah.
No, but 2L. Wait, what?
No. I just want to
2L
see
minus
what
2n.
we need to show.
Yeah, 2L minus 2n, I think. Because you have 2L.
So complexity of XL is L plus n.
N plus L.
And complexity is 2n here.
Okay, so
So
L minus
the
n.
difference should be L minus n actually. We need not to show that it is 0, but show the bound L minus n. And what we can do for this?
Can you write, I mean, because it's not clearly, can you write
Yeah.
n minus n more clearly, please?
N minus n, yeah.
Okay.
And this would be good for us. That's what we need.
Yes. So, and before the idea was that there is just a single, so before the complexity was just 0 because there is the only line of low complexity.
Single line of this complexity goes through that.
Because otherwise we can describe the point given a line through another line with
Yeah.
lower than n bits.
Yeah.
Now you want to show maybe that there are at most 2 to the L minus n such lines?
Yeah, exactly. You can show that there are at most that many lines because the points that have more lines going through these points of this complexity, there are only a few of them. Indeed, it's a valid argument, and we can do it. But there is a completely stupid argument which strangely works. And this argument goes like that. We don't need to do anything. We know that for line of complexity n minus some c log n, always have a point of complexity to n. And of course, this argument is relativizable. So it's true for every oracle.
Yeah.
So we have a line of complexity bigger than n. Let's find some oracle that decreases this complexity up to n minus c log n. Of course, we can just take for example, the shortest description of this line and take some prefix of it as an oracle.
Yes.
So if you have freedom, you can make complexity any complexity between 0 and original complexity. So you can have the complexity n minus c log n, oracle complexity.
Yeah.
Then you can point, as we already know, that in this case we can find the point of complexity to n minus something, almost to n.
Yeah. So, and then
now it's an oracle complexity. But of course, the complexity without oracle can be even bigger, only bigger. And the maximal complexity is 2n. So there is no... We will have complexity 2n.
Mm-hmm.
This is extremely strange because we replace some kind of computation, this and that, by this strange oracle thing. It's one thing which I completely confused. What does it mean? Why does it work, and how can we use it? It seems to claim some obvious cheating, but I don't see what is the source of this cheating, what we essentially do here.
May I ask a relevant question? Hello?
Yeah.
Yep. Do you remember that in your combinatorial argument in this inclusion principle, you reduced some situation the size of the set somehow artificially. You took vertices in a graph with a maximal possible degree,
so you
but
mean
not all of them.
taking an oracle is just replacing a set by a subset?
No, I'm not saying it. I'm asking whether it is the same trick, or these are different tricks that has nothing to do one with another.
Yeah. But so what is the suggested answer?
I have no. It's a fair question. I don't know.
Yeah, Laurent, Kolya, Sasha, and What do you think? It's the same trick or different trick?
No idea.
No idea.
Yeah, also no idea.
Okay, but so now we are completely ready to understand the proof of Don's result. So a line of complexity L smaller than n has points of all complexities between L and L plus n.
You again say about lines in finite field.
Finite field f of size 2 to the n, and we have a two-dimensional plane so a line L has points x of all complexity L and L plus n. Okay, now the question, if Don, if you have a tablet or you want to explain the proof yourself.
So unfortunately, I don't have a tablet.
Okay, you can dictate to me, or you can just wait and suffer hearing how I explain your proof.
No, please go ahead.
You prefer to suffer, okay. So actually there are three cases. So one case is just very simple, the case where we know already the argument. So actually, let me draw the picture. We have 0, n, to n, we have L here, and we have L plus n here. And the first case works when we are close to maximal. So looking for a point of complexity L plus k, when k is quite close, not too far from n. And this is exactly like before. So let's take a point which is independent of L. Or its first coordinate is independent of L. We know that this is the same. Then complexity of the pair XL is indeed L plus n, which is the same as the complexity of the first coordinates and L, by the way.
So again,
and in
coordinates, what
Sorry?
are x's? I'm lost. Are we the first x is a point or a coordinate or what?
No, first big X is a point.
Yeah, I mean it's not
And small
it's
x,
not seen where are they big or small, to be honest.
okay, there are points just with two segments and points with which are curved.
Okay, so you take the point on L, which is maximal complexity given.
Yeah, we take a point of maximal complexity relative to L.
Yes. Then
So the
complexity
pair
of the
has
pair.
complexity L plus n.
Yes.
No.
By the way,
sorry.
can you
Sorry, it's not what we want really. We want to find a point of complexity L plus k. So let's take a point of complexity.
Can I ask maybe
conditional complexity k.
just to understand the previous argument? Was there any reason really to consider this coordinate? Why couldn't we just start with the point that has maximal complexity on a line given L?
No, the only reason is what Vereshchagin suggested, to consider the first coordinate. No.
And now we need the first coordinate.
No, we don't need the first coordinate.
Let's do without the first coordinate.
Okay, let's do without the first coordinate.
Okay.
Kolya will forgive us for that. So now we consider the point which has complexity, conditional complexity k, and the pair has complexity L plus k.
So why does it exist? It's a stupid question.
No,
Well, if I may
every
interject,
set-
still the
every
sorry,
set-
if I may interject, still the reason to consider one coordinate is to argue that we get n and not anything different from that, right? It's a because technically when you take a point on the line, it could have very high complexity. So you have to argue why you get n and nothing else. And the reason it's because it's if you know the line
No. If we have a set, any set, then in this set, of course, we have, if we consider conditional complexity when the set is given, in this set we have points, elements of all complexities between 0 and at log cardinality.
Okay, because of the cardinality. Yeah, okay. Yeah, you can also do
It
that,
can
I
be,
guess.
and
So
then
can
we
you
can
explain
choose
why
what.
for stupid people? Once again, why does it hold? So the claim is that if you have set of some sides, then conditional on this set, there are points, there are elements of any given complexity, more or less.
Yeah, because
Well, it's just
conditional on the
counting.
set, the set is simple itself.
Yes.
And so it's more or less the initial segment of initial numbers or whatever.
No, but can you please give some argument? Just to maybe...
Okay. Imagine that we have strings of length n. Do you need some argument why there is a string of any complexity?
Maybe I need, but, or I mean, maybe
Okay.
I can just shut up and think for 1 minute and you can continue. But maybe if you can just say the argument for one, which is one sentence, it maybe would be helpful.
Okay. So imagine we have some set A. I don't know, with A elements. And the question is why there are sets of points of all elements of all complexity between 0 and log A. Because consider, for example, first elements of this sets.
Okay, so you say you take the first 2 to the k elements in some enumeration, computable enumeration, and then they all have complexity
Take first 2 to the
k
k elements. They all have complexity at most k plus log or something. And most of them should have complexity exactly k, because there is not enough elements of smaller complexity.
Yeah.
So for a simple set, the spectrum is trivial somehow in all cases.
Yeah.
Okay. So what it remains to show that again complexity of x given L is 0. No, if L given x is 0. No. And why? Imagine there is another line, L prime, that goes through x.
Complexity L.
And complexity of L prime given L is at most k.
This argument works when when L is smaller than k, something like that.
Yeah. No, let's see it. So
no, I mean, then you say that there is a unique line L of complexity at most L that passes through X. Because if there is another line
of complexity at most
L, small L.
That goes through X. Because if there is another line L prime, then knowing L and L prime, we can reconstruct L and X. Let's just.
No, I mean,
because X is the only point, intersection point.
Yes. So given L, you can describe X by just describing L prime, and you get less than k bits.
We can describe Lx given L by describing L prime given L. We can describe the pair Lx just knowing L and L prime. And this is complexity L plus k.
Yeah,
and
okay.
this has
You
complexity
like to
L.
talk about this sum. I just was talking about the conditional complexity of x given L. But okay.
Okay, but it's important the conditional complexity. It's important the complexity is conditional, but generally we cannot reconstruct x knowing xl prime. We need to know L also.
Yeah, so knowing L, I can specify x by giving L prime that requires just k
Yeah.
bits. And if k is less than, sorry, just L bits.
L
So,
bits. And
so if L
if
is less
L
than
is
k, it
smaller,
works.
Yeah. So here we have L plus, actually we have 2L here and L plus N. So for this part, this works.
Yeah.
And this is case number 1. Case number 2 will be here. But are there questions about case number 1?
No, what can you
So we just
specify?
repeat the
Case
same
number
argument.
1 is case what? When
When
k
k is
is
greater
what?
than L.
When k is larger than L. Okay. So k number 2, case number 2 is when k is smaller than L, or it must L.
No.
No.
K number 2 is actually when k plus L is smaller than N. So it's another regime. It's a small increase.
And there will be just two cases.
Before we have increase almost by N, and now we have small increase.
So I have a stupid question. There will be just two cases.
No, because there are something here, so we need third case. But I want to consider simple cases first. So there are two regimes when no, actually, if L is smaller than 1/2, then these two cases cover all possible cases. But if L is closer to N, then there is a third case.
Yeah, okay.
Okay. And so what to do if k plus L is smaller than N? And then here is, we need to recall what Vereshchagin told us, that we need to consider the first coordinate. So consider x, first coordinate, that is random, not random, its complexity of x is just k plus L. So since k plus L is smaller than N, we can just find the chord and set a string of this complexity.
Yes.
But of course, we want now that the point has also this complexity, which is not guaranteed because the point contains more information than the coordinate. But so assume that complexity of L given x is 0. So we just take all information that is in the line, and which is L bits, and then just add random bits until we get a string of complexity k plus L. So we take the first coordinate of the required complexity and additionally require that this first coordinate determine the line. This is when miracle starts. I cannot understand why we do this, but if we do this, it works.
But then you say that probably the point has the same complexity as the coordinate.
Yeah, of course, because now the first coordinate determines the line. And so the complexity of the point is the complexity of its first coordinate, is the complexity of the point and the line, and whatever, and everything is k plus L. And we are done.
Yeah.
Wait. Why we are done? So what was
Okay,
our
so
goal?
So first, do you agree that we can find a point with these properties?
Yes.
And then complexity of not a point, a coordinate with this property. And then complexity of the point.
I see how to prove all these inequalities. And what
that's exactly what we need. We need a point of complexity k plus L.
Really?
No, we have a line of complexity L, and we want to find a point which has complexity k plus L.
Okay. Now I got it.
Yeah. So this is the second case. Is it clear?
So
Bruno, if you are still here, is it clear?
Yes. This is easy case.
Yeah.
I mean, but then, like in all these cases, it's like you're not using the full, like the argument fully. I mean, like in one case, maybe you could play on the conditional that L prime could be only easy conditional given L or something. Here you just, I don't know. But okay, let's see the field
So
case.
I see that you are unhappy, and I agree with you, but I don't understand your specific complaint that I am not using something fully. What I don't use fully.
So, Sasha, the second case, it is just that you take the code for the line and you add something that is random relative to it of length.
Yeah.
Okay, I understand.
Yeah. No, that's exactly what Don wrote, but I suggest we look at more general informational picture. We have some kind of line which has L bits, and we just add k bits here, and all this becomes our x. But essentially what you say, we take the shortest code and we add independent random bits to it and get whatever we want. So this is a bit strange. We take the line, we compress this thing, and then we apply the formula of the line to the compressed version of the line. Sometimes people in cryptography, when instead of taking random bits from the oracle, they apply what they have to the compressed version, to cache version of something or something. But here it's strange. Okay, so can we move to the third case? Let me try. Maybe we can even keep something. Actually, the third case will also cover the first. Okay, so let me draw again. So we have a line between L0, N, and 2N. We have some L. We have L plus N. And so we have, here we have case number 2, and here actually the same length. We have here case number 1. And so we need to have case number 3, which will actually cover all this. So we don't need actually to consider case number 1 separately. We can start with case number 3. So the case number 3 is just very simple case when the increase when k plus L is great. Oh no, maybe let's cover number 2. Okay. Let's start arguing. So k plus L is greater than n. Yeah. No. So actually we have case number 3 and case number 2, that's enough. But
Yeah.
so what do we do? And of course now we cannot have x of this complexity because it's too big. It's bigger than n, so we cannot find the coordinate of this complexity. But still we can have the same picture. We have complexity L, and we want to increase it by some k. So let's find a string of complexity n minus k. This will be x. And this will be line L. So in other terms, let's take the shortest description of line L. Let's keep n minus k bits from this description and add some new completely random k bits. In this way we get a point of complexity n, which is maximally independent from L. And then take...
Wait, what? But how is it like maximally possibly independent?
So we take shortest description of L.
Yes.
And then it is by itself, it's smaller than
Okay, we take
L.
n minus k bits from this description, and we use the fact that L is larger than n minus k, and then we add k
So
node.
something remains. So it remains this difference, k plus L minus n. We take n minus k bits from the shortest description of L.
Yeah.
And add k random bits.
Yes.
But now what I say that we don't use L completely, there is something which remains.
Yes.
And still the claim is that complexity of x is exactly k plus L. So again, complexity, if we have a pair x, small x and L, which has the same as a big X and L, it is by construction, we look on this diagram, by construction we have L and we add k bits. So it's k plus L.
Yeah.
And again, we need to show that complexity of L given x is small. And this will be all. And here is the trickiest part of all this argument. I really cannot imagine how you can get to this idea, but so let's denote this common part of L and x by z and claim L is the only line that goes through x and complexity of L given z is smaller than k plus L minus n. So this is our main claim. No, complexity
Minus
of
what?
our L. Sorry?
Minus what? W?
Minus n.
N. Ah, this is n.
K plus L minus n is just, no, we have some, what is complexity of L given z? It is just the part of L which doesn't get into z. And the size of this part is k plus L minus n. Because here we have n, and the total size is n k plus l. So what remains here in this zone is k plus l minus n.
Yeah. It is the only line that goes through X such that L given Z is at most
K plus L minus, it is at most what it is for L.
yeah.
So if it's the case, how can we reconstruct L given X? From X we can reconstruct Z because Z is a part of X here.
Yeah.
This picture. And knowing X and Z, we just enumerate all lines that we look for a line which goes through X and has this complexity given Z. So if we know this, then we know the bound for complexity. So it remains to prove this fact in the box. Yeah? I agree that it looks strange, but
So given X, how many bits we need to describe?
No, say it again.
No, I mean, before the contradiction somehow was that if there are more than...
Yeah, you think about how to prove this.
Yeah.
So why it's true. Okay, imagine we have some other line, L prime, which has these things, and L prime goes through X.
I guess you should somehow say that the complexity, then given L, you can describe X shorter than it's supposed to be by describing L prime somehow.
Then if we know L and L prime,
we can
then we know, of course, L prime and X, because X they are intersection point.
Yes.
And if we know L, how complicated is L prime? If we know L, we also know Z, because Z is a part of L. So we can add here Z.
Yes.
And L prime is simple given Z, so it's smaller than complexity of L plus complexity of L prime given Z.
Yes.
Complexity of L is L, and complexity of L prime given Z is K plus L minus N. And complexity, this determines L and X, and therefore complexity at least K plus L. It's just exactly K plus L. No, we should get some contradiction now. It's always the place when I'm confused.
L is
L
less
is smaller
than
than
n. L minus n is negative, and we have a contradiction.
Here it's written K plus L minus n. And here it's written K plus L. And the contradiction is this is negative. Yeah, exactly.
Wait. So again, so X has complexity K plus L.
It's by construction because Lx is just this. We know that this is the same as X, small xl, it's K plus L.
Yeah, but then you can describe it by L, A prime, and X.
x.
You can actually describe it just by L and L prime.
By L prime.
So you give L with small L bits.
So if we know L, we also know Z automatically. And so it's enough to describe L and L prime given Z. Which is this?
A plus L minus N. Okay.
So this is the argument.
So
So
I
are there some questions why it works?
I have some
Yes.
doubts. Somehow you have these cases when k plus L is less than n, and when k plus L is larger than n. And
Isn't that
somehow
the
you
problem
assume
when
that they
k-
are smaller and larger by some log n that you would require in the argument.
Yeah.
So
Then
wouldn't be there any problem when k plus L is exactly n? I don't know.
yeah. Yeah. But you already heard my idiotic argument with oracles.
Okay. So what?
So now it's in a different flavor. You take an oracle to decrease the complexity only slightly by several log n.
Of what? Of
And
everything?
you take a simple you get a simple oracle.
No, but decreasing complexity of what? Of L of the line?
Of the line. No, because there is a problem when k plus L is exactly n.
Yeah. So you want to say you decrease the complexity a little
I can
bit,
decrease the complexity of L a bit.
and then you get some point that of required complexity, but with this
Yeah, but to
small
decrease
oracle.
complexity by logarithmic term, it's enough to have an oracle of logarithmic size. So now the oracle doesn't matter at all whether there is a complexity. No, you want to say that it's idiotic thing and only mad people can do this. Yeah, I agree.
No, I'm
It
not.
should have some
It's
meaning, but I don't
somehow
understand.
some kind of.
Yeah,
Probably it's true. I don't know.
yeah. I can also show the application of this idiotic argument to prove something. So imagine we now have other case. We have a complexity of L, for example, 1.1 n. And we want to find a point x on L of complexity, say 1.5 n. So this is open question. But I will show how you can get a partial answer to this open question. And probably you guess how do we do it. Let's add some oracle which will decrease the complexity of L to just n. And then we know that this case is already covered by Don's theorem. So we can find oracle, we can find complexity of any complexity we want. And let's take it complexity 145n. And then without oracle, it's somewhere between, the oracle has complexity 1.1. Wow, what is happening? I did something. Without oracle, we have complexity 145n, and with oracle has complexity 0.1n, so the complexity is between 155, 155n and 145n. So we can have a complexity which is quite close to we want, but not exactly 1.5 which we wanted. So that's I can say also that I tried to apply this argument to do something in general for the case when complexity of line is bigger than n. And maybe one can try to find the combinatorial version and prove it using some probabilistic argument, or you can try to do something like this, or you maybe try to do something based on continuity. So the problem is that there is no continuity. You cannot say that if you move a point along a line slightly, then complexities change only a bit. Because one coordinate complexity changes a bit, but the another coordinate can change significantly. Like with line which goes through 0, 0, when we switch to any other point, the complexity makes a jump. So there is no continuity. So now I guess we have two questions to Don. First, how can one came to this argument? And second, what to do when the complexity is greater than n?
Yeah, so the first question, I'm not sure. I guess once you have the idea of lowering oracles, you just start playing around, and it feels natural to me, but I don't know. Maybe.
So you thought. So you started with the idea that you need to use some oracle, and then you somehow came to this argument. This
Yes.
is what I didn't understand.
No, but I don't understand. Can I ask before, like, is it that so is it also a separate theorem about finite fields that were proven also by Donald before, and you took the argument from there, or you were reading the? I didn't understand. So, or you was like you said.
No.
You were trying to understand this proof about lines.
Things are perfectly simple. Don't send me this as one page with this argument, and then I tried to look at it for a very long time, and finally I understood it. And then I tried to explain it now. Nothing else.
But this was for finite fields.
For finite field, no.
But it's still open. I mean, it's just literally open, or you just didn't understand what happens with L larger than n.
No, for me it's literally open, and for Don, I think he also says this. Maybe some clever people in the world know this, but we are not aware.
Okay, no. But I mean, just want to clarify the situation. About what is open, what is not. I mean,
No. My idea is that some of you will look at this and realize that the tricks are enough. In some combinations are enough to consider the general case.
So and the situation, so this was all done in Euclidean space. So this dimension spectrum that Sasha described at the beginning for points in R2.
Yeah.
And actually in R2, this dichotomy is also present where the line has a large dimension. You have to split into cases depending on whether the line has large dimension, like greater than 1, or small dimension, less than 1.
So you mean the original theorem for dimensions?
Right.
For Hausdorff dimensions of points in the real line. Not as the approximation thing, but just the original theorem.
Right.
Yeah.
And the analog is dimension 1 lines corresponds to the complexity of the line is greater than n. Yeah. And so this is also present in R2 and is actually the harder case there as well in R2.
Yeah.
And the only way to get around it, so the way we can get around it in Euclidean space is it depends on the topology of R2 actually. That you have this sort of continuity, that close points must have close dimension or complexity. So it's really a topological argument in R2, and that's the reason it doesn't extend to the finite field case.
But what is very strange in R2, that if we consider the approximation version for R2, then just the possibility to increase complexity by n doesn't work anymore.
Right.
So what somehow it seems that it's very essential that you use the slim inf. So without the slim inf for finite case, this is not true. And this is what makes me almost hopeless to understand this proof, because if you don't consider finite case, what else can you do? What are the other tools? And this is a thing.
Yeah, I'm sort of split. It wouldn't surprise me if this actually didn't work in arbitrary finite fields for lines of dimension greater than n, that you could find lines of dimension greater than n where there are gaps.
Yeah. So you say that you can imagine a line of dimension 1.1 n when there are gaps of size maximal length 0.1 n, but not more, because of this oracle argument.
Well, finite fields are weird. I don't know. I know that there are the finite field geometers have been studying kind of versions of this, and things aren't always as pleasant as maybe they should be. So,
but then I can say something like this. So if you explain that, look, finite fields are complicated things, and there is a combinatorial conjecture which, I don't know, Tao and other people solve for 10 years and cannot solve, and our question is equivalent to this combinatorial conjecture, then at least we will know that what is the problem. So there is a complicated structure of finite field. So this we can make an excuse that, look, it's not our business. Let's wait until they solve this problem. But it would be nice at least to formulate the question in terms of finite fields. What should we know about a finite field to be sure then that this exists? What Andrei says that if we just want to find a pair of a point of a line which has some properties in terms of complexities and of terms of common information, this can be somehow translated to a statement about finite fields. This is a kind of satisfactory. No, it's not satisfactory, but at least on our small, before we get a Fields medal, we cannot attack this problem. But still, it would be nice to have a reason why, or at least you have this strange argument with three cases. Maybe there is some combinatorial translation of what do we do really in this argument. That's what I hope to hear at some point. Okay,
actually, your argument is two cases. Has two cases. The first case
one of the cases is covered by the other one.
Yeah. It was introductory to connect with the previous proof.
But what I should say, in the first case, actually, we can consider the same combinatorial argument. We can consider on every line some set of points, and then to prove that one of these points should have big complexity because there's not other lines cannot go through it. So this first case can be translated into combinatorial language, it seems to me. But to others, I have no idea how to do it.
Yes, the third case looks a magic and has no clear combinatorial meaning. And by the way, I have a question. As I see, your argument can be extended to low-degree polynomials. If you consider a graph of low-degree polynomial, the same should be true. You should add some terms depending on the degree of polynomial. But okay.
Now, also,
Yeah.
there is another natural extensions. So we actually have a kind of 1 and 2 dimensional subspaces in a projective space. And then we can ask, for example, imagine there is a plane. What are the maximal complexities of line on this plane? Or general question, we have a graph, which is kind of a bipartite graph, which is kind of reasonably uniform. So for example, for every point has the same degree and it's edge transitive. So for example, this can be points and lines. This can be spaces of this dimension and subspaces of other dimension and something like this. And the general question, so we have some characteristic of the graph. What are the complexity spectrum of among the neighbors of some point? For example, if a graph is transitive and edge transitive and uniform and fixed degree, is it true that every two edges of the same complexity have points in the same complexity spectrum? Andrei, maybe you explain something different, but maybe you can say this too. Oh, we don't hear you. But
No, I don't know.
So if the answer is positive, it's quite strange. We have an edge transitive graph, but still some vertices have different properties. It's very hard to believe how it's possible.
But actually, in this talk, you discussed properties you discussed pairs, a line and point where complexity of each of these objects is not maximal. Then it's, naturally we can say that not all lines have this intermediate complexity. Not all points are like that. Not all pairs are like that. So this would be not that surprising.
So you say that the two vertices in one part of the graph can be, they are combinatorially indistinguishable, and they also have the same complexities, but they have some different properties in terms of complexities of neighbors. It would be interesting to understand how it happens and why it happens. Another graph is we just have a fixed Hamming distance between binary strings of given length.
No, this is I'm sure this is a more difficult question. This is a complicated graph with complicated structure.
Yeah, this is a much more difficult question. But this is somehow what Kolya and Sasha somehow consider. Imagine we have a string of given complexity and want to change d points, d coordinates. What is the maximal increase in complexity you can achieve? Or what are the possible increases? So it would be also, I think, something at least is known. And I remember that Sasha Kazachinsky even explained something about this once, but I forgot exactly what he explained. Okay, any questions? And then a question to Don. How much time you need to explain this theorem about infinite lines? And now you more or less see our abilities to understand arguments. How fast can you go? And so how much time you will need, and what are the possible schedules for which is convenient for that?
I think an hour and a half to maybe hour, anything between an hour and 2 hours, I would be happy to do.
No. If you will accept we need 3 sessions for 2 hours,
okay,
I can say maybe it's a bit not enough, but it's reasonable. But now you see that you don't have even the slightest idea how it would go. I guess. Okay, but when can you start then? So normal
Tuesdays
days is Monday, but it seems that it's not good for you.
Mondays are really tricky for me. Tuesdays at this time are good in
Are
general.
good.
Yeah.
But for example, Laran, which said that this time is good for you, is it, if you are still here, or maybe not, because
I don't
he
think he
has
is.
to fetch his child. But what do we think about this time? For example, next week, Bruno says okay. Kolya, Andrei, is it okay or not?
Just to give-
Georgi.
This time next week,
Yeah.
right?
Yeah.
Yeah, this is good for
Yeah. It's okay.
Yeah. Kolya, is it okay? Or Kolya disappeared. Okay, so Sasha, next week this time is okay?
Yeah.
Yeah.
For me, no.
Yeah, for you. Yeah, of course.
No. For me, I cannot do this time next week.
Or just because of next week or in general?
Just
Tuesday
because
is
of
not-
next week. I mean, I'm replacing somebody like in some lectures.
Okay, then maybe in 2 weeks.
Sure.
Tuesday.
Just
So-
2 weeks.
So we'll have a
Because
seminar
actually on the next
on
week,
Monday and on
Vereshchagin
Tuesday.
did not send. Sorry?
But what's the plan? Maybe it's to have a seminar on Monday and then on Tuesday. Because in 2
No.
weeks,
Next
we
week
have a
we
talk.
have a seminar on Monday with students of Vereshchagin.
Yeah,
So
and in
this
2
is
weeks we
more or less
have
fixed already.
also a
And-
talk on Monday.
In 2 weeks? No,
Yes.
I don't know whether we have a talk
Yeah, we
on
will
Monday.
have. I mean, we will have this talk about preservation theorems by Zhemislov, the guy from Oxford.
Okay, but still, I guess we can survive a talk on Monday and Tuesday.
But Donald can only do on Tuesdays.
On Tuesday, this is the problem.
But maybe we can do in 3 weeks on Tuesday because, like, probably it would be hard to
Okay.
or not.
But are you sure we will all be alive in 3 weeks?
No, you could ask the same question about 1 week.
Okay, but just the probability will be a bit. No, so 2 weeks. No. If you really cannot do it in 2 weeks, what people think?
No, I mean, but I can skip in principle. I don't. It's not.
No. That's very important theorem, and who will explain it to me later when I don't understand anything? It's not.
No, I mean, it's just I thinking why not like now we want like we didn't have a seminar for like 4 weeks or somebody, and then we were putting 2 seminars on the same week. I guess it's not a right strategy now. Then if we have different talks, let's put them on different weeks. I don't know what the rush, or is there a rush to understand this?
No. Just no. But I will tell you, this is not the last seminar about this, because definitely we will need several sessions to understand this. So the earlier we
I
start,
mean,
the more
then
it's
let's
good.
do it in 3 weeks, I guess. On Tuesday in 3 weeks. Would be it fine?
Fine. Yeah, I can also do Thursdays are also good for me. So, whatever's Tuesday or Thursday, whatever's best for everybody else.
Okay, so let's agree. This is 19 May, Tuesday. Yeah, Sasha, that's what you're
No.
suggesting.
26th of May, Tuesday.
26th of May.
Next week we
sorry.
have students pre-defenses. In 2 weeks, on 18th of Monday, we have a talk about preservation theorems. And then on the next week, maybe on 26th of
Okay,
May.
so if you can understand only one thing a week, then there is no choice. So we make.
No, I mean, I'm
26
just saying that like there was a situation where there was no talks for, I don't know, 3 or 4 weeks.
Actually, I prefer to have no more than one talk in a week.
Okay.
Yeah. For one
So
seminar.
Don, 26 is okay for you.
Yeah.
So we started, but then as a kind of maybe if there is a chance